So thank you everyone for being here. I'm very excited to be giving this talk to you about gravitational waves. It's kind of what I spend my PhD doing. And my goal would be that like by the end of this talk, you have some idea of what gravitational waves are, why maybe you should care about them, and what you can learn scientifically from them. So yeah, without further ado, I know I'm like the talk between you and the telescopes, and it's a very clear sky today. So I hopefully will get you excited for that. Let's get right into it. So in terms of what we're going to cover, we're first going to cover very broadly Newton's laws of gravity and motion. Then I'm going to introduce to you what gravitational waves are, what they might look like. After that, I'm going to talk to you about the detectors that we use to sort of see gravitational waves. We call this the LBK, or the LIGO detectors. Following this, I'm going to highlight some of the data science techniques that we use to analyze what gravitational waves are, what we can learn from them scientifically, and what they might look like in the future. And then finally, I get to talk to you about my research, which is gravitational wave cosmology. It's like a subfield of gravitational waves. So yeah, without further ado, let's get started. And let's just directly get started with Newton's laws of gravity and motion. Newton predicted, hundreds and hundreds of years ago, 200 years ago, that if you have two objects and they both have some, weight or mass associated with them, that they should attract, and that this attraction should sort of be proportional to how heavy these things are. This was what he called the force of gravity, and this sort of explained why we are stuck to the planets, why the Earth orbits around the sun, and sort of different celestial mechanics in general. But Newton wasn't really the first person to think about this. In fact, there were like many people before Newton who thought about gravity and how different objects worked around one another. We have sort of the Italians down here. We have Aristotle, and then we have some other philosophers, some from India, and then they sort of met in the Middle East. And then following that, we sort of have the field of gravity being born over here. Now, this in itself can be a lot. So for the purposes of this talk, I'm mainly going to focus just on the last two. In fact, I'm actually just going to focus on the last one, which is Einstein. And that's basically what I'm going to talk about in terms of general relativity, how we think of gravity, and gravitational waves. So I gave you a long spiel about like how gravity works in terms of what Newton thought, and that if you have these forces, they should attract one another. But then Einstein came along and he said, Newton, you're actually wrong. There's a few things that you thought about that I disagree with. So Newton first postulated that space and time are actually two different things. But then when Einstein came along, he said, you know what? They actually don't need to be different for that matter. Like we could actually say that they're actually just the same thing, and there could be a way of explaining that. So like an example I like to give is if you say how far away the CN Tower is, you could say, oh, it's 3 kilometers from here. But you could also say it's 20 minutes. So depending on how you describe things, you can sort of link space and time together. And that's kind of exactly what Einstein did. He formulated this general theory of gravity. He called it general relativity, and that sort of explained how things spoke with one another. So he had his equation for general relativity. I know this is a complicated equation. You don't have to worry about it too much. Basically, what you should take away from his theory is that he said there's a relationship between gravity on one side of the equation and matter on the other side of the equation. And those two things should be talking to one another. And in fact, they're the same thing. So if you have something that's very filled with matter, it's the same as having a lot of gravity. So like a good example of this would be if you have like a star orbiting in a circle, you can see that as it goes around in a circle, it actually warps the space-time around it. So as the star goes in a circle, you can see the actual fabric of space-time changing as it goes in a circle. So that sort of was his theory of general relativity, and it sort of answered a lot of problems that came out of Newton's theory. And one of the things that sort of fell out of his theory of general relativity was gravitational waves, which is kind of what I do, is what I spend my research doing, and it's what my PhD's on. So then we sort of reach the question, what are gravitational waves? Like, what even are they? That's a great question to ask, but before going into that, I'm going to talk a little bit about what are waves more generally. There are many different flavors that waves can take. They can take different shapes and sizes. So for example, you can hear sound waves. As I'm speaking to you, they're arriving at your ear. You can see light waves, which is basically how lights from stars will reach us through these light waves. You could also have seismic waves. So these seismic waves are basically waves that actually propagate through Earth itself, and then we sort of detect them through different seismometers. You can also get water waves. So for example, this is a dragon boat going through the water. And as you row through the dragon boat, you're sort of changing little ripples in the actual still water. And from that, you're going to get water waves. So I think the point that I want you to take away from this slide is that there are many different types of waves. And gravitational waves are just another type of wave. So similar to the water wave over here, gravitational waves are just changing the ripples and fabrics of space-time. So when you ask the question, what actually is a gravitational wave, it really is just a small change in the fabric of space-time itself. So what you're seeing here are like two stars or really dense objects like black holes orbiting one another. And as they go around in a circle, you can sort of see changes in gravity itself as they orbit and then reach us. So what you're seeing here are gravitational waves. Now, when you look at this in like more detail, it might sort of seem cartoonish, and it's not exactly what we see in the universe. That's very valid. This is a more realistic simulation for what a gravitational wave might look like. So what you're seeing here is a black hole orbiting around a really, really dense object called a neutron star. I'll talk about those later in the talk. But they sort of get closer and closer, they orbit faster and faster, and then they merge. And then when they sort of collide together, they emit this really powerful pulse of gravity, and then it sort of all calms down after that. So what you have just seen is a black hole merging with a really dense star. So yeah, that's one example of what it might look like. We could sort of look at what it looks like from the top down. So again, now we have two black holes. We have like a big black hole and a small black hole, really, really dense objects in the universe. And as they orbit one another, they sort of emit a little bit of change in gravity, and then it gets swallowed, and then you get a really loud ripple of gravity. So we could take this exact picture and turn it vertical, and you would see something similar. So this is the black hole going right in front of you and right behind you. And what you end up seeing is like a ring right behind the bigger black hole. Einstein actually predicted this. He called it Einstein's ring. And again, they merge, they collide after a certain amount of time. So that's great. You might ask me, well, what does a gravitational wave even look like then? You've just been showing me a bunch of black holes colliding. I would say that's a great question. Gravitational waves are sort of hard to show in 3D space, but the best picture I can show you is sort of this one. So you can sort of think of the net you see here as like the fabric of space-time. So when a gravitational wave goes through what this is, you can sort of think of it as a wave propagating through the fabric of space-time itself. Now, this is in 3 dimensions. What would this do to like a circle? What would this do to the Earth? Well, this is an example of how gravitational waves would affect a circle. It would sort of give you 2 different vibrations. You'll get like a cross type of vibration, and then you'll get a plus sort of vibration. This is what it looked like when like you have a gravitational wave and you pass it through a circle. Now, again, this is sort of like a cartoonish picture, so I thought it might be useful to show you what this would look like to Earth. So, okay, here we go. We have the Earth, and what we're going to do is we're going to send a loud gravitational wave through it. Now, this is not to scale, but as the gravitational wave goes through, you can sort of see it wobbles the Earth a little. So the wobbles get stronger as the black holes get closer and closer. And then we sort of see like a little big wobble at the end. Now, obviously, this is not to scale, but this is sort of what the Earth would experience when a gravitational wave passes through it. So just to prime you for later on, you can almost think that if you have a very, very accurate ruler, like somewhere along here, you could sort of measure how distances change. And if you could do that, maybe you could detect these things. So hold on to that thought. I'll come back to that later. Um, I've showed you a very like scale exaggerated version of what a gravitational wave is. So I'm just going to show you a to scale version of what it might look like. So we're going to go from the Earth and we're going to zoom in. We're going to zoom in really, really close all the way to the atom. So now you're looking at an atom, it could be a hydrogen atom, and you can sort of see the cloud and the electron orbiting it, and the nucleus is in the center. So when a gravitational wave passes, it'll change the size of the atom itself. How much? Well, if we zoom into the nucleus here, okay, we keep zooming in. Okay, we've reached the proton. Okay, now we're looking at the edge of the proton. This is how much a gravitational wave will change the size of a proton. It is tiny. So the changes are 1,000th the size of a proton. So if we have any hope of detecting these things, we better have a really, really good ruler. So people in the 60s thought of this and set out to make a really, really good ruler. And 50 years later, boom, we have one. So this is called the LIGO detector. It is a gravitational wave detector. And how we do this is we basically have the home station here. We take a very, very loud laser, like one of the most powerful lasers in the world. We shoot it down 4 kilometers in a vacuum tube. We hit a mirror. It bounces off the mirror, comes back towards us, and then we can detect changes in the distance of what this is. So if a gravitational wave passes through us and literally hits the Earth, we can detect a change in the distance, again, the thousandth the size of a proton, and then we're in business. So that's great. Turns out that's not as easy as we thought it would be. There's a lot of noise. So if someone like starts their car engine here, that would change the results. If there's like a plane flying over, that would change the results. Turns out this was near a military base, so that was a big problem. If there was a small earthquake, then that would also change the results. So there's a lot of noise, and we need to find a way of like dealing with this noise. So what do? Well, we build a second one. We take this and we copy and paste it and build a second one. So then what we do is if we see a signal in one, that's cool. If we see it in both, okay, maybe they're not related to each other. Maybe it can't be a plane flying over. If we do see it in one, it might still be a signal, but maybe we should look at it more carefully and sort of try to understand what's going on there. So there you are. This is the birth of the LIGO detectors. It's called the Laser Interferometer Gravitational Wave Observatory. It's a mouthful. Everyone ever just calls it LIGO. So there's 2 of them on opposite sides of the states. There's one in Washington State and there's one in Livingston, which is just like an hour away from Louisiana State. So there's 2 in the US, there's 2 in Europe. There's one in Japan, but it turns out Japan's actually not the best place to put a gravitational wave detector. There can be a few earthquakes. There's also another one planned for India. That one should go up in the next 5 to 10 years, hopefully. So we're starting to build up a network of gravitational wave detectors. So that's great. How do we measure the changes in the distances? I just told you, like, okay, we build a ruler and then now this ruler measures distances. How does that actually even work? Well, I'm glad you asked. How it works is we basically take light, really powerful light, we send it down the 4-kilometer arm, it bounces, and then it comes back, and then it combines again and reaches our detector. So again, what you're seeing here is light. We split the light up in intensity, so 50% one side, 50% the other. It hits off the mirror, it comes back. So the same thing's happening on that side. They recombine, and then they hit the detector. So notice that, yeah, it's really cool. Notice that right now, the light sort of cancels each other out. But if you have a small change in any of the distances, they don't cancel each other out. So we can use this technique to sort of pick up tiny, tiny changes in distances through bright spots and dark spots. This is called an interferometer. And that's kind of why we need two arms. We can't just use one arm and use a very accurate ruler. We need to actually split the light, send it down one end, send it down the other end, recombine it, and then you're in business. So that's sort of the crux of how we're getting a signal from it. And what it would look like when two black holes merge is sort of something like this. So you sort of see like brighter spots and darker spots, and it sort of changes as the black holes are merging. So you sort of have some gradual change, and then as the two black holes get closer and closer, they start to wobble faster, and then once they merge, it's just quiet. So this is called the merger. That's the technical term we call for it. So that was like the core of how the LIGO detectors work. And I think what you should just take away from this is that there is some phenomenal technology being used here. We're pushing the quantum limit with engineering and our lasers. And we're also testing, really powerful lasers and very powerful mirrors. That's been quite abstract. So I think what we should do now is just take a quick step back and think about what we've actually just seen. So black holes merge all the time. So this particular black hole merged 1.3 billion years ago in a galaxy far, far away. And then that signal traveled through the universe for 1.3 billion years. And then here on Earth, on 14 September 2015, it hit the detectors. So it hit one of the detectors, and then 10 milliseconds later, because gravitational waves have some speed, it hit the other detector. And at first we thought, okay, maybe this was not like a real signal. We're just seeing it in one here. Oh, okay, we saw it in another signal. Okay, this is a little more interesting than we thought it would be. We overlapped the signals, and then, oh, they exactly match. This is crazy. We've detected gravitational waves for the first time ever, almost 100 years after Einstein predicted them. So this was a very, very groundbreaking discovery that we could finally observe them and see how they work. And it got a lot of notoriety in the news. So the grand architects for the detector, Raynor West, Barry Barish, and Kip Thorne, they ended up winning the Nobel Prize in 2017 for physics for their contributions to the LIGO detector and the observation of gravitational waves. So we were able to detect them basically. Yay, go us. But after that, we haven't stopped. So we've sort of been working on overdrive, and we've had more and more runs to observe more and more gravitational wave events. And we've been working harder and harder to see out to further distances. So this next plot you see here is sort of the three main detectors we have now. So at first it was just LIGO, then the Italians joined us, and now the Japanese. And what you should just take away from this plot is that we've had multiple observing runs. We've had 4 of them. And if you notice where we are right now, we're actually in the middle of our 4th observing run. So if my phone goes off and I have work to do tonight, then we've observed something from gravitational waves. So you might say, okay, good job, Akash, you've observed something. Is it a lot of things or just a few things? And I would say it's a lot of things. So just as a reminder, before 2015, for all of humanity, we had 0 gravitational waves. 2015, we had 1. This is how long we've been observing in days. So, by around 2017, we had a handful, maybe 10. Now we're pushing 300. So just in a span of 10 years, we've observed hundreds of gravitational wave events. So this is a very, very exciting time for our field because we're in that stage now where we're really getting to define what happens in gravitational wave astronomy. And it's only going to get better and better. And for the next few years, we have some detectors planned that should hopefully give us even more events than this. So you're thinking like thousands of events now. So the universe is going to sort of go off like popcorns. Like we're currently getting one like every 2 to 3 days. We're going to get one even faster. How are we going to do this? Well, it turns out Earth is not the best place to put a gravitational wave detector. So what we're trying to do is take the detector we have here, make some upgrades, and then put it in space. So if we put it in space, there's no seismic noise, there's no humans. It turns out humans can be a problem. And then we sort of have these gravitational wave detectors in Earth, in space, which we can sort of observe more things and we can observe the things better. So that's great. That's sort of the big summary of where we stand with gravitational wave detectors. And if you're going to just take away one thing, you should take away the fact that we've just started an era of gravitational wave astronomy, and we have so much more to learn in terms of science, and we have so many more events to see. So now I'm kind of going to switch gears a little, and I just sort of told you we have so much more to learn, but I haven't told you how we actually analyze any of this data. So, how do we analyze this data? It's a lot of data to deal with. Well, the answer is data science and statistics. It's a lot of data to go through. So without this, we wouldn't be able to sort of extract useful information from it. Now, this is where I spend most of my time in my PhD. So I could talk to you about this for a very, very long time. So I'm gonna not do that and stick to two things that hopefully I can get the point across with. So yeah, the two things we're going to talk about are like extended versions of Monte Carlo simulations. It's called Markov chain Monte Carlo, MCMC. And the other thing we're going to talk about very briefly is neural networks, which is sort of what powers ChatGPT. So if you take neural networks, you modify it a bit, you get something called a transformer, you stack them, you get a large language model. So yeah, before that, MCMC or Markov chain Monte Carlo. I use it, and I know that a lot of people in the astronomy department use this method. It's sort of an extended version of a Monte Carlo simulation. So if you just take random changes, that's what a Monte Carlo simulation is. And it's widely used. So it's not just used by astronomers and physicists, although a lot of us have used it, but it's used by, cancer research, hedge funds, climate modeling, neuroscience, and betting odds. So it's really widely used. So if you're going to take away one thing from what an MCMC is basically it's something that can be widely used in many different things. But what is it? I've been tossing this word around like a lot in the last minute, and what even is that? Well, you should sort of think of it as like tinkering. So you're turning knobs until you see something that you like, and then you look at that a little more. So you should see that you're turning the knobs. Okay, there's something you don't like. Don't look at that. Turn the knobs a little more. Oh, this is interesting. Okay, fine tune your knobs, and then before you reach the end, you sort of reach the final version. So the example I like to give is sort of like if you're a photo editor in Photoshop, you can keep tweaking all your tools until you have the perfect picture you need. You need the raw data, but from the raw data, you sort of do some fine tuning, you do some tweaking, and then from that, you get the perfect picture. So great. That's an example of what an MCMC actually does. In reality, it is a little more complicated. So the next slide is more of like what I do in my research. And it's quite complicated. You start off with some theorems, Pythagoras theorem, Bayes theorem. You have some acceptance rejection steps, more complicated math, and then it gets out of hand really fast. So don't worry about all of that. Right now, just think of it as like a tool where you're tinkering knobs and you're learning cool things about the universe. So what does this actually mean for gravitational waves? Well, I told you that we're trying to learn science from this. We're trying to see like, is there anything useful we can learn about the universe from gravitational waves? Well, what is the first thing we'd want to know about these black holes? I don't know, maybe how heavy these are, how far away they are, cool things associated with that. So that's kind of what we do. So we have a prediction, we turn some knobs, and then we try to match our prediction with what the actual data is. So what I'm showing you here, the blue is the data and the orange is the prediction. And it's kind of hard to see, but these parameters here are the mass and distance of the event. So as you sort of tune these knobs, you change the masses and you change the distance, but you get a better match. So as we look at it more and more, our match improves until finally we get a fairly decent match, and we're happy with what our overlay is. And then there you go. We have the masses, we have the spins, we have the distances. And that's great because now we can start to do science from that. So looking back to that event I just told you from a galaxy really, really far away, it was basically a black hole that was 30 times the mass of the sun, merging with a black hole that's 35 times the mass of the sun. And then we get a black hole that's 62 times the mass of the sun. Now, for those of you that realize there's 3 solar masses missing, good job. They sort of propagate as energy. So the gravitational waves that we observe are literally 3 times the mass of the sun's worth of energy. A lot of energy. So this is an example of what we use the tool MCMC for. And it's a really widely applicable tool. And if there's one thing you take away, you should take away that MCMC is used basically everywhere. MCMC is not perfect though. It turns out there are some drawbacks associated with this method. It is quite time consuming. And when I say time consuming, I mean when you make it run on a supercomputer, it could take weeks, maybe even months to run. So it's not like the perfect way of doing things. And these weeks and months takes a lot of energy. So it's not ideal. So there are other ways we can do things. And what I'm going to show you is just one example of using a neural network to make this learning the masses faster. This next slide is the most technical slide of how the neural networks work. So I have a video up there to help you if you find it useful. So this is basically the whole architecture of our neural network in terms of how we analyze the data. I am going to simplify it down just a bit for you, so we'll get rid of all of that. We start with some gravitational wave data over here. Then we do some data compression. It's a fancy word, but basically what we do is we just take the data, make it smaller, and make it more understandable. So it's called data wrangling. After that, we do something that's very unique to gravitational waves. It's called a frequency masking. It's a clever stats trick. That's all it is. After that, we apply neural networks. So the type of neural network we apply is called a residual network. It was first developed in Microsoft, but it's been like widely used in other places now. And you can think of neural networks as sort of learning things automatically. So again, if you have ChatGPT, that's an example of a very complex neural network. So we have ResNet, which is a neural network, and then a normalizing flow, which is, again, just another complicated name for some sort of neural network. Neural networks, that's all you need to take away from this. And then after that, we have just a Monte Carlo simulation. So at the end of all of that, we get astrophysics. So that's great. We finally got an astrophysics, and now we can learn about science. Great. But I actually haven't told you anything about the science yet. What science can we actually learn from gravitational waves? Well, there's many different parts of science we can learn from gravitational waves, and I'm just going to cover a very few small section of them. But hopefully this will just give you a flavor for the type of physics and astrophysics we can do from them. So the first thing we can do is we can test general relativity. So Einstein predicted the theory, hundreds of years ago, and now based on what we see, we can see if there's a match between observations and what we think is correct from theory. The current status of this is that as far as we can tell, general relativity works, and it is consistent with all our data. So that's great. Another thing we can do is learn about the densest objects, or the densest stars in the universe. So these are neutron stars. If you were here for the last Astro Tours where Ayush was talking, he talked about these things as well. And these are really, really dense objects, like really dense. So like if you take a small chunk of a neutron star, it would probably be the same weight as Earth. So it's really heavy. And so one full neutron star is approximately the mass of 1.5 suns. But the distance across a neutron star is tiny. Like a neutron star is maybe like 12, 13 kilometers across. So we could literally fit a neutron star between where we are right now and Canada's Wonderland. So very, very dense, heavy objects. And what that allows us to do is probe what's happening at the heaviest densities. So it's so dense here, in fact, that we cannot recreate this laboratory on Earth. So this is sort of the only way we can test what's happening at these high densities. So that opens up a lot of high energy astrophysics and particle physics that we couldn't otherwise study. Another thing we can do is learn how really heavy elements like gold, platinum, uranium, plutonium, they're all formed. What you're looking at over here is a kilonova. It's kind of like a supernova, but just slightly smaller, and it happens with neutron stars. So when we have these events in the universe, it's possible that gravitational waves will detect them, like our detectors will detect these things happening, and then we can point our telescopes at the sky and learn about it. And why this is interesting is because there is a group of astronomers that believe that most of the elements like gold, platinum, etc., have to have come from these sort of events. So anything lighter than like oxygen, you can get from many, many different things. But especially the really, really heavy elements, you have to have had a kilonova or some sort of rapid neutron capture process. It's called the rapid process or the R process. You have to have had that happening in the universe. So if obviously on Earth we can refine gold or refine other things, but if you go and see an asteroid in the universe and it's like rock solid gold, you should think that must have come from a kilonova. So that's one cool thing we can do scientifically with gravitational wave detectors. Um, in 2017, we detected two neutron stars colliding, and because of that, we could tell the astronomy community where to point their telescopes, which was great. Another thing we can learn with gravitational waves is different types of galaxies. So, we are special, but Milky Way is not the only type of galaxy there is. There are other types of galaxies, and there are black holes in all sorts of galaxies. So, by studying how these black holes work in different galaxies and their properties associated with them, we're able to learn a lot about the science of galaxies, where different sort of how much mass they have and how far away they are. So there's a lot of science you can do with galaxies with gravitational waves, and in particular also with how far away they are. A third thing you can do, or a fifth thing actually you could do with gravitational waves is called gravitational wave cosmology. Now, this is what I do for my research. And it's sort of, when you think of cosmology, you should sort of think of it as like the history of the universe, how we got to where we are and where we're going in the future. So we started off with the Big Bang, at least as an astronomy community, we believe that. And then we had, you could start observing light at 375,000 years after that. And then 400 million years after that, you had the first stars. And then these stars took a while to clump together, and then you have galaxies coming out after that, much, much later. So this is our 13.77 billion year universe. And because gravitational waves happen at many different times in the universe, we can sort of see how this changes with distance. And by seeing this change in distance, we can learn about the science of the history of the universe and how things change. So that's basically an update for gravitational wave cosmology. And that's kind of where my research comes in. I look at this particularly, and I look at what we can learn with gravitational wave cosmology. So what I do for my research is I take all these black holes that merge. There's hundreds of them now, remember? And I use some data science, and then I sort of try to figure out the composition of the universe. So in terms of what the composition of the universe is, I mainly look at how fast the universe is expanding, and that'll tell us how this composition changes. So just to give you some reference for what the composition of the universe is right now, we're about 5% atoms, so me, you, stars, planets. Then we're about 25% dark matter and 70% dark energy. But these numbers aren't constant throughout the universe. Like if you look back a billion years, these numbers would be a little different. If you look back 10 billion years, these numbers would be really different. So right now, most of the universe is dark energy, but not too long ago, most of the universe was actually dark matter. And really long ago, most of the universe was just light. So there are different phases in the universe which dominate, and what I look at is how this is expanding and how the expansion will tell us what will happen in the future. So that's like a quick summary of what I look at in terms of the universe itself. But when we look at how fast the universe is expanding, there's actually a problem that's starting to emerge in the astrophysics itself. And we call it the Hubble tension or the expansion rate tension. Kind of what happens is that we sort of can learn the expansion rate of the universe, but what happens when you go into the future is that the data sort of starts to give you questions. So when you look at this plot, you should be looking at the red and the blue and how much they overlap. So in the year 2000, we were doing great. We were so happy. There was overlap. Everything worked out. 2008, same sort of thing. They sort of disagreed a little bit, but you can see the error bars. Okay, they fall within one another. Okay, we're okay. 2016, yeah, no, this is a problem now. So we start to look at the error bars. They're shrinking for both sorts of experiments. And these are not just like groups of 5 people. There are like literally thousands of people going into each one of these numbers. So it is like a very, very big community that's working on this. And it's just growing further and further apart, which is interesting to say the least. Now, you might look at this and say, oh, Karsh, maybe it's just some stats thing. Like you guys do a lot of stats. Maybe you've like underestimated your error bars and like it's just some stats. I wish. We've tried to look at it in greater detail, and we find that there's actually now like a 1 in 4 million chance that this is just statistics. So it's disagreeing pretty strongly now, and we are working on it basically. So there's a greater than 5 sigma or a very, very high chance that there's something going on here. And why this might be exciting for us is that it might be a reason to show that our understanding of the universe might not be fully complete. If this is correct, and if we haven't done something wrong, then there might be some actual physics going on here that we need to look at in greater detail and sort of try to understand. So uh, yeah, what my research sort of tries to do is take gravitational waves and put an extra constraint here on what the expansion rate is. So I'm sort of, as a gravitational wave person, I want to put an extra thing on here and say, okay, we think it's actually this thing with gravitational waves, and this agrees with the red or the blue, and now because of that, we can put this question to the end. That was actually, in theory, what we set out to do. In practice, it's not as good yet as we hoped. This is currently where gravitational waves are. So the error bars are very, very large. In fact, they're even larger if you make more loose assumptions. And right now, gravitational waves are not very constraining on where the true expansion rate is. But again, we are just at the start of this gravitational wave era. So hopefully these error bars will shrink a lot with time, and we will be able to help you make a statement on if we're in the blue or the red or maybe somewhere in between. So that's basically all I wanted to cover in my talk. That sort of concludes where my research is. So I'll just quickly summarize, and then I'm happy to take some questions. Yeah. So in summary, what did we learn? We learned about general relativity. We learned that Einstein, had these ways of thinking, and it was different from Newton. And out of that, predicted gravitational waves. We learned about the detectors, really, really cool rulers that could measure distances. And because of that, we can detect gravitational waves from them. Then we learned about some data science. We learned about MCMC, we learned about neural networks, and we could learn about what they are at the core and how we can learn science with them for gravitational waves. After that, we use these methods to learn about astrophysics. And from the astrophysics we learn, we talk a little bit about my research, which is gravitational wave cosmology, and the tensions that are currently existing in the field. So thank you very much. Thank you all for being here. And hopefully, well, not hopefully, we do have clear skies and the telescopes are on the 14th floor.
Wonderful. Well, we have a good amount of time for some questions. I'm just going to bring lights on. So let's start right here in the blue.
I understood that there was a conflict between the two methods of predicting the expansion. What I wasn't clear about was what the two methods were. I knew what was blue and one was red.
Yes, very, very, very good. Yeah, very good question. So the question was, what are these methods and how do they even work for predicting the expansion rate? So the first one is called the CMB, Cosmic Microwave Background, very technical term, you don't have to worry about it. But how that works is you basically directly go back and try to see as far back as you can when light was first emitted from the universe. And between then and now, the light will have expanded with the expanding universe. And that's how we get to see how much the universe has expanded. The other one is called the distance ladder. Now, the way the distance ladder works is you sort of measure a small distance, which you think you're pretty confident about. And you know the distance from that small distance to the next thing, to the next thing. So if you can sort of think of it as like if you're seeing lampposts on a street, you know your distance to like the nearest lamppost pretty well. But then you also know how far each lamppost is from another. So you could just count the number of lampposts and be like, okay, it's like 20 lampposts, so that's how far away we are. So those are the two ways of measuring the expansion rate. There are other ways, but those are the two most popular that people quote. Hopefully that answers your question.
And right there.
Yeah, that's a very, very good question. The latitudes don't make a difference for our detections because the gravitational wave detector can basically see everything above it and everything below it. So ideally, we do want to put it in like many other places, but it turns out that where we put the detector, we need to make vacuum tubes. We need to make sure that the maintenance is okay. We need to make sure that the temperature is reasonable, that we can keep these mirrors in relatively good shape. There are other detectors being planned, and for example, LIGO India was being planned, and it's good because it sort of cancels out some of the dark spots that our detectors observe. So yeah, to answer your question, there's no specific latitude, and the detectors kind of just observe everything above and everything below us.
Let's do all the way over there. Yeah.
Explain bubble parts. And do you like mean that it could be split as in the gravity waves are manipulating space time and that's why the bubble parts itself is different.
Yeah, so what I meant to say with that is the gravity waves can explain if we're either in the red or the blue sort of paradigm. Are we saying that the CMB people are correct, or if we're saying that the distance ladder people are correct? The gravitational waves are not going to affect the expansion of the universe that much. But as they merge billions of years ago and they travel through the universe, they will expand. And based on how they expand, we can learn about the expansion rate of the universe.